So, welcome back. We continue with the proof that the generator G is Q adjoint. Okay. So, it is again easy to check that G is densely defined. So, here is the dense subset of that is a subset of dg, and closed operator you directly verify. Okay, write down the condition on that what is meant by an operator closed. Okay, so I just concentrate on these two things. So, G is skew symmetric and on this. Okay. So, just so the first, so let me write G is skew symmetric. So, what we have to show? We have to show is G x, not G x. So, let me, because we are dealing with functions. G f G, this inner product in H is equal to minus f g g for all f g in d g. Okay. So, for that you just take, let f equal to f1 f2 and g equal to. So, to begin with I take this g1 g2 to be smooth functions. I want to integrate by parts. So, that is where I need, but they are dense. Okay. So, that is what we are going to use. So, now let me write that what is the this G f G in H. So, let me write that this is. So, this the components of G f are f 2 Laplacian f1 and the components of G are G1 G2 and that inner product is in H, and by definition that is integral grad f2 dot grad G1. So, again you may put the complex conjugate there, but I am not doing that, plus this is Laplacian f1 G2. Okay. And I am assuming that G2 is in CC infinity. So, I can integrate by parts and this will give me okay, let me just write grad f2 grad G1 minus, so this grad f1 grad G2. I am integrating parts and there are no boundary conditions because G2 has compact support. Okay. So, this holds for all G1 G2 which are in C infinity. Okay. So, by density this result holds, this equality holds for all G in dg. Okay. So, let me call this as just 1. Okay. And similarly, now you consider this f dg, consider f g g. Again, to begin with, you assume f1, f2 are in CC infinity. So, now f1, f2 and you have g2 Laplacian g1. Okay, so, this is integral left f1 grad g2 plus f2 Laplacian g1. Okay, and now here I want to integrate the parts first. Okay, so, this will give you, this is minus grad f2 and grad g, and again you extend by density to all f in dg. So, we get here this grad g2 minus grad. So, this is 2. Okay. Now, just you compare 1 and 2, you immediately see that. So, G is skew symmetric. Okay. So, this, for example, here this integral grad f1 grad g2 is negative sign, and here it is a positive sign, that is fine. Okay. And the next one, okay, just to show plus or minus 1 belongs to the resolvent set of G. Okay. So, essentially we have to solve. Okay, let me just so given G in H, we have to discuss the solvability, of this plus or minus I minus G f equal to G for f in. So, we have to get in dg. Okay. Now, you write again f equal to f1 f2, okay, and again use the definition of G. So, what you get is, so let me just write that. For example, taking first plus sign, okay. So, you get f1 minus f2 equal to g1 and f2 minus Laplacian f1 equal to g2, and if you add these two, what you get is f1 minus Laplacian f1 is equal to g1 plus g2, and if you take minus sign, so similarly you get f1 minus Laplacian f1 is equal to g1 minus g2. Okay. And you have already studied in the elliptic part of this course. So, at least so if g1 g2 belong to again C infinity C, we can obtain the solutions f1 and then f2. So, f1 minus f2 is g1. So, f2 is obtained from, and then f2 also. using Fourier transform. Okay, so this you have seen it many times. Okay. So, for if the right hand side is in smooth class, we obtain a solution f belonging to the domain of G. Okay. So, what does that say? So, this implies the image of plus or minus I minus G contains this, which is dense. In H. So, that means the image is dense. Okay. So, by my earlier remark, so that shows, so therefore, image of plus or minus I minus G is dense in H. Okay. And that proves G is skew edge. Okay. So, write down the steps in detail. Okay. Maybe for the first time you are seeing all these unbounded operators and other things. Okay. Write down all the steps carefully to understand in a better way. Okay. Okay. So, that so by Stone's theorem, G generates a unitary group so let me call it UT. In scattering theory of the wave equation, they denote it by U0T. It is a free space, there is no obstacle. When wave equation is considered in with obstacle, then they denote it by UT, but since we are not doing that, so I call it UT. Okay. So, again let me recall. Okay. So, what does this mean? This means U inverse T is nothing but the adjoint of T, and in this case it is also U of minus T. Okay. And norm of UT equal to 1 for all T, and norm of this is like Parseval relation. So, this for all F in H, that Hilbert space and all T. And this is what gives us, as we see, leads to because this norm in the Hilbert space is precisely the energy norm. So, that gives us conservation of energy. So, if we choose the domain of G differently, we may still get a group generated by it, but then we may not get this conservation of energy, which is a physical requirement. Okay. So, any other domain, if you consider, it can only be partially correct. Okay. But then how this is connected to wave equation? Okay, connection with, finally we have to show that, right. So, here we do not see, we only see that operator G, and now there is a unitary group, okay, but how it is connected to wave equation. Connection to, of course, everything has originated from there. So, we should able to connect to wave equation. Okay. So, again by general theory of semi groups we developed, this happens. Okay. So, let F belongs to F belongs to DG. Okay. Then this mapping, with this we have already studied, this going to UTF is differentiable. See how the general theory is helping us, and this relation we have d by dt of UTF. See, as of now we know only the existence of this unitary group, but we do not know what is this UTF in terms of F. Okay, so that is not clear, right. But when we restrict F to certain subspace, namely this subspace of the generator, then we have this UTF. Of course, this is, we do not need that, this is also true. Okay. So, for the time being, just temporarily you write that this UTF, so UTF1 F2, just write that UTVT. Okay. That is the this is mapping from H to H itself. Okay. So, this, so just G U T V T. Okay. So, this is, if you use the definition of this G, you get this V T Laplacian, right. But this is what? This we have not done that. So, this is what shall I write? Okay, this is just du by dt, dv by dt. Okay. So, now you just equate the respective components. So, you immediately see that so therefore, so we have V is equal to U t, okay, and V t is equal to Laplacian u, and that of course implies U t t So, the first component of this operator so the first component, namely U t, becomes the solution of the wave equation. So, therefore, the first component of UTF represents the solution of the wave equation. Okay. So, in fact we get little more. So, let me just say that thing. So, in fact we obtain more, we get more info. Okay. So, what is that more info? This Laplacian u, if you again look at the, just keep on looking that. So, when f is in dg, so this Laplacian u, the second component, is in L2. Okay. So, we have the Laplacian u is in L2 of Rn, okay, and that implies del square u del xi del xj also in L2 for so recall that I already commented in the one of the previous classes. So, it is very important that here we are working in L2, okay, and in Rn. So, we can use the Fourier transform and get it, and I do not know whether this is true if p is in LP, p not equal to 2. Okay. That is one thing. And d by dt of UTF, this is again in the Hilbert space H, and that implies del square u by del t del xi are also in L2 for 1 less than or equal to. Okay. So, finally, so UTT equal to Laplacian u, because that is what we obtained, and that implies UTT is also in L2. So, these are some kind of regularity we obtain on the solution. So, all these derivatives are in L2, and this is what we require in the energy estimate. So, let me just recall that we did okay. So, recall this energy estimate, which was proved under the smoothness assumption. This energy of u in B0 R is any positive number at any time t is less than or equal to E of u B0 R plus t at 0, and similarly here. So, the main ingredient here was using the Green's theorem on that cone. Okay. So, this R minus t. So, R is bigger than t, okay, whatever time we choose there, and again at 0. Okay. So, this energy estimates, this estimate now holds for. So, this was proved under the assumption that u is smooth by taking the initial conditions smooth, but now with all this conclusions on the solution, u and all its second derivatives and of course first derivatives are already there. Okay, so okay, that is part of the definition of the space H. Okay. So, this estimate now holds for the solution. Obtained from semigroup, obtained from UT. Anyhow, conservation of energy is already there, but even this estimate, this is local, right? This is you are only getting the energy at a local ball. So, even this estimate holds for that solution. Okay. So, I just want to this I continue in the next class. So, what I do is, so next time. So, now consider this is another choice. Okay. This H has H1 cross L2. Okay. So, so this is of course typical of wave equation. So, the first component namely that F1 F2 is always have one extra regularity than the F2. So, if F2 is in L2, F1 is in H1. Okay. So, this is one possibility. Okay. So, this is a possibility. Okay. And now same G is same. Okay. So, 0 identity Laplacian 0 and now dG is just H2 cross H1. Okay. So, here also it is possible to so it is possible to show that G generates a group okay. And in fact, it is not unitary. If it is unitary, then we get conservation of energy, but now the space this H1. Okay. So, there is already the L2 norm of that function comes into play. Okay. So, we do not get so, but the conservation of energy is not satisfied. So, the moral of the story is that there could be many choices for the a certain operator with certain domain. So, it can generate a semi group or even a group, but it may fail to satisfy certain physical requirements. Okay. So, one should keep these things in mind while applying this abstract theory of semi groups. Okay. So, next time I will take up this again on the wave equation, but now with this setup. Okay. It is similar, but the computations are bit lengthy because now we do not have that. See, last time we just in this case we just showed that G is a skew adjoint, but now we have to obtain the spectral estimates, resolvent estimates. Okay. So, resolvent estimates are a bit difficult. okay, but it is worth doing. So, let me just show you are difficult, because now we do not have that square jointness. Okay. So, we have to obtain the resolvent estimates, and again there we use the elliptic theory and Fourier transform and other things. Thank you.